New pictures from the James Webb Space Telescope have stunned researchers. As opposed to extending our understanding of the universe, these pictures uncovered a disturbing reality. Our ongoing comprehension is insufficient to grasp the possibility of the universe in its starting stages. Where the hypothesis of the universe's starting point shows up at its limits, this urges us to ponder new hypotheses about its beginning. The question arises as to how the universe was shaped comprehensively, and why this new revelation challenges even the most experienced space specialists to sort out more about the Big Bang and the dynamic nuances of the discovery. We ought to review the possibility of the Big Bang itself. Contrary to popular thinking, the Big Bang was not an impact in prior space. Rather, it was space itself that began around 13.8 billion years ago, along with matter and time. From an extraordinary quirk in actual science and cosmology, this idiosyncrasy describes a state where gravity is so intense that the curvature of spacetime becomes infinite. Today, following billions of years since the beginning of the universe, we see that our vast home is part of a significant communication for experts. This represents a critical part of the universe since its very presence. Its evidently ceaseless extension is important to appreciate. The universe isn't wandering into prior space. Rather, space itself is ceaselessly extending in size, according to conventional hypothesis. The first stars began to shine somewhere between 200 and 300 million years after the Big Bang, marking the end of the supposed Dark Age. This was when the first luminous celestial objects bunched together to form mature galaxies. However, how quickly these systems developed remains an incomprehensible conundrum. A significant piece of data arose through the first pictures caught by the James Webb Space Telescope in July 2022. Subject matter experts revealed that the telescope had identified various galaxies, some of which had already existed around 300 million years after the development of the universe. However, compared to the vast structures that formed billions of years later, these early galaxies were significantly smaller and less massive. This fits perfectly with the scientific model accepted by experts. The density of matter in the early universe was simply not adequate to lead to galaxies the size of those observed today. The discovery of 6 astonishing redshifted luminous spots from James Webb ended up triggering one of the most significant astronomical crises of recent times. In spite of the fact that these recently discovered worlds are comparable in age to recently recorded galaxies, they are nearly as massive as our own Milky Way galaxy. This has created an intriguing mystery in cosmic science. After examining a series of images captured by the near-infrared camera, experts identified the recently mentioned light sources. Using redshift analysis, they confirmed that the light from these objects took more than 1 billion years to reach our eyes on Earth. Consequently, we are dealing with structures that had already existed somewhere between 570 and 700 million years after the confirmed Big Bang. By examining the characteristics of these designs, it was inferred that the Webb telescope had captured 6 early galaxies in the image. Amazingly, these galaxies were so massive that they defied traditional assumptions of cosmology. Rather than finding the usual dwarf galaxies, structures were identified that were nearly as large as our own Milky Way, despite having formed early in cosmic history. If we continue to analyze the data collected by the James Webb Telescope, this gravitationally bound assortment of stars was already more than 10 billion times the mass of the Sun at that time, with one possibly astounding instance being 10 billion solar masses. However, whether this possibility is deemed a mystery isn't completely settled. Even in this scenario, there would be significantly more mass in the early universe than previously anticipated, presenting a riddle. The identified objects contradict nearly all conventional cosmological hypotheses. Even if only one of these systems turns out to be genuine, it would challenge our past assumptions to explain the presence of these structures. Additionally, the density of matter in the early universe would need to be several times greater than previously acknowledged to make sense of this peculiarity. Another similarly unusual explanation relies on the possibility that these galaxies formed in a way that is still entirely opaque to us. These revelations and the discussions they provoke about the Big Bang lead more experts to distance themselves from this hypothesis. Many astronomers with alternative viewpoints are confused, and their perspectives are often heard in scientific journals. Even those who express doubts about existing theories are frequently labeled as eccentric. However, it is clear that even experts who still defend the Big Bang hypothesis are constantly faced with questions without clear answers. These inquiry questions include specific issues such as why and how, 13.8 billion years ago, something literally arose out of nothing. Could something genuinely start from nothing? Or was there some triggering event? Or was it all an accident? Stephen Hawking pointed out that the concept of time as we know it began with the Big Bang. Consequently, this process could not have been triggered by something else or by an external reason. A similarly vague question relates to the uniformity of radiation and density throughout the universe. Regardless of which direction or at what distance we look on a larger cosmic scale, we find comparable densities and distributions of galaxies, nebulae, and radiation everywhere. Conventional specialists explain this peculiarity through the theory of cosmic inflation. However, various experts extend this assumption further with a theory of turbulent inflation. According to this idea, inflation has only stopped in certain areas, like bubbles, and continues vigorously elsewhere. This suggests that various universes could form in these bubbles, each with its own unique physical laws. Within this model, a crucial question emerges. What if the universe doesn't represent the totality? More creatively, what if another universe existed before our own? In that case, the Big Bang would become part of a larger cycle. According to this viewpoint, our universe is part of a larger complex structure. Within this model, the possibility of a timeless pattern of decay and resurrection of the universe is advanced. However, this isn't the only perspective introduced in the field of cosmology. Apart from the theory of how things came to be, in 1955, for example, an article appeared in NASA's Big Times arguing that there may have never been a Big Bang since the universe has existed for an endless period. In this view, the development of the universe would be non-existent, and the continuous evolution of matter could give the impression of constant growth. Moreover, another interesting controversial speculation comes from the realm of quantum physics and string theory. Some experiments have suggested that our universe and everything in it might be a projection or a higher dimensional simulation. While this could seem like the plot of a whimsical science fiction film, it could be connected to the Kardashev scale, which measures the degree of development of a civilization based on its capacity to harness energy. If there were a Type 3 civilization capable of fully using the energy of an entire galaxy, it could have created a perfect simulation. However, understanding reality in such a scenario is a deeply complex matter. Exploring the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new pictures captured by the James Webb Space Telescope have reignited discussions about the very fabric of our reality, testing established theories and provoking scientists to reconsider essential elements of cosmological understanding. At the center of this inquiry lies the hypothesis of the universe's origin, a foundation of modern cosmology. According to this hypothesis, around 13.8 billion years ago, the universe arose out of an extraordinarily thick and hot state, expanding rapidly and resulting in space, time, and matter as we know it today. This immense event was not merely an explosion within prior space, but included the absolute beginning of space itself. The concept of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, supports our understanding of this early stage. Yet the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how quickly structures formed in the universe's infancy. These galaxies, identified within a few hundred million years of the Big Bang, appear surprisingly mature and massive when compared to current cosmological models. One of the key questions raised by these discoveries is the concept of cosmic inflation. According to the prevailing theory, inflation occurred within parts of a second after the Big Bang, causing the universe to grow exponentially. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, current findings suggest complexities in the early universe's evolution that may require adjustments to inflationary models. The emergence of galaxies like those seen by the James Webb Telescope urges cosmologists to reevaluate the conditions and processes that govern the universe's early history. These galaxies, now significant in size and mass just after the Big Bang, suggest a density of matter that exceeds previous estimates. The mystery broadens when considering how such massive structures could form and evolve in such a relatively short cosmic time frame. Moreover, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy. two elusive components that comprise most of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the conventional Big Bang perspective. Some theories suggest that our universe is just one among many in a vast multiverse, each with its own unique physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One thought gaining traction is that of eternal inflation, where universes continuously emerge from a larger inflating space. This hypothesis posits that our universe could be just one bubble among countless others, each with its own distinct properties. The challenge lies in finding observational evidence to support such speculative ideas, as they push the limits of observational validation. Another provocative theory proposes that our universe exists within a simulated reality akin to a computer-generated simulation. This concept draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with remarkable fidelity. If true, our perception of reality as a distinct physical universe could be fundamentally altered, raising critical philosophical and scientific questions about the nature of existence. Furthermore, advances in observational astronomy continue to reveal the universe's vastness and complexity. Telescopes like the James Webb Space Telescope, with their remarkable sensitivity and resolution, promise to unveil even more secrets of the universe. Future observations may shed light on the earliest moments of the universe, providing insights into its ultimate fate and the fundamental principles governing its evolution. Beyond observational astronomy, particle physicists are exploring the fundamental particles and forces that shape the universe. The mission to unify gravity with the other three major forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central goal of theoretical physics. In the realm of quantum mechanics, the concept of time itself remains a topic of intense debate. Quantum theories suggest that time might be emergent or even elusive at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our understanding of the universe's origins and evolution. Moreover, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars beyond our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. In addition to these scientific endeavors, cultural and philosophical reflections on the universe enhance our understanding of our place within it. Inquiries about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration drive exploration and discussion across disciplines. As we stand on the verge of a new era in astronomy and cosmology, powered by technological advancements and theoretical breakthroughs, we are reminded of the profound interconnectedness of everything, from the smallest subatomic particles to the grand cosmic structures spanning billions of light years. Whether exploring the depths of black holes, mapping the paths of distant galaxies, or contemplating the nature of reality, each discovery brings us closer to unraveling the intricate tapestry of the universe. As we venture further into the cosmos, guided by curiosity and driven by a desire to grasp the universe's vastness and complexity, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment encapsulates the essence of scientific exploration, a continuous journey of discovery, wonder, and enlightenment that continues to inspire generations of researchers and thinkers alike. In the words of Albert Einstein, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science." As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of both the universe and ourselves. Thus, the exploration of the universe is not merely a scientific endeavor, but a profound human quest for knowledge and meaning, an adventure that transcends the boundaries of existence and invites us to contemplate our place in the grand tapestry of being.